Welcome back everyone to 11.10 Taylor and Maclaurin series. Last video, let's get to it with some examples. So we have a nice, relatively easy function here, e to the 4x. And we want to find the nth term Maclaurin polynomial for f using, well, we're actually going to do it in two different ways. The first way is going to be with our definition, and then we're going to use a theorem. So notice we have an nth term Maclaurin polynomial. This is more in line with what you're likely to see on your web work homework, right? So they're more interested in the nth term Maclaurin polynomial or Taylor polynomial rather than the series. But okay, so let's look at this definition really quick. The definitions gives us the coefficients in front of our polynomial, and then we have our x minus a to the n. So, okay, seems relatively straightforward. Let's go ahead and start taking some derivatives. Again, we need to try to get a good formula for the nth derivative of f, and this time we're going to be evaluating at 0, right, because it's a Maclaurin polynomial. So again, we need a general formula for the nth derivative of f at 0. Okay, so let's go ahead and start taking some derivatives. Well, the function itself is just e to the 4x. When I take one derivative, I'm going to have my e to the 4x times 4. Take a second derivative, I'm going to have e to the 4x times 4 times 4. Right, so here's the 4 along for the ride, and then it's going to be 4 squared, really, because another 4 comes down, thanks to chain rule. And then we can guess the third derivative is going to be 4 cubed e to the 4x. And now if I plug in 0 in all of these cases, let's see, the first one's going to be 1, and then 4 to the first power, and then 4 to the second power, and then 4 to the third power. If you'd like, we can rewrite 1 as 4 to the 0 power. And now hopefully we can see a nice pattern here. It always seems to be whatever n is, right? N equals 0, 1, 2, 3. It always seems to be 4 to that power. So it's 4 to the nth power. So if I want the nth degree Taylor polynomial, right? So n really needs to be our maximum term here now. Well, this is going to be summing from I equals 0 to n. So we change our index variable to I here. Right? And we need the ith derivative of f at 0 in our case. So the ith derivative, well, let's just take our 4 to the n and replace n with I. Divided by I factorial times x to the I, and boom, we are done. So there we are. That is the nth term Maclaurin polynomial. Didn't ask for a radius of convergence, anything like this. Okay, moving on. I want to compare it to this method, right? Find the nth term Maclaurin polynomial for f using a theorem. So our theorem here, it tells us what the Maclaurin series is for e to the x, right? So e to the x, we already know that this is a sum from n equals 0 to infinity of x to the n over n factorial. So let's go ahead and try to use this. But now instead of x to the I, I'm going to use u to the I over I factorial. And we'll see why I do this here in just a second, right? So this is approximately equal to e to the u, right? We haven't talked about remainders, so that's why I'm using approximately and stuff. Well, okay. So now what should our u be, right? Well, in our case, we're trying to model e to the 4x, right? So u should be 4x. So let's go ahead and try plugging that in there. Again, we get this from up here. Our function is e to the 4x, so it's really like e to the u. That's how I know that u should be 4x. Okay, so this is the sum from I equals 0 to n of 4x, all raised to the I over I factorial. And now let's imagine if we expanded this out, right? If we were to distribute this raising to the I power. So this is I from 0 to n, summing these all up, of 4 to the I times x to the I over I factorial, and lo and behold, my goodness, these are the exact same answer. So you can see that we can actually use the theorem, Theorem 11.10.7, to derive Maclaurin series for more complicated functions, like we have here. So it's important to kind of know this table and be able to use it to generate other Maclaurin series, or, as we saw here, Maclaurin polynomials. Okay, I have one more example. Before we get to it, I need to tell you a little bit more about remainders. Okay, so again, we've defined this remainder thing so that when we add it to the nth degree Taylor polynomial, we get the function itself, right? So hopefully, if we're doing a good job, then the remainder should be relatively small. That is, the higher the Taylor polynomial is, the smaller the remainder should be. So if we take the limit as n goes to infinity of our remainder polynomial, we should hopefully get closer and closer and closer to the zero polynomial because, well, the Taylor series should be doing a good job. Okay, assuming that we're in this radius of convergence. So the distance between x and a should be less than r. Okay, so the Taylor remainder theorem gives us a way to calculate out the remainder. So r sub n of x is given by the n plus first derivative of f evaluated at some c over n plus 1 factorial times x minus a to the n plus 1. Right, so you can see this has a lot to do with the n plus first term of what would be the Taylor polynomial. Okay, so where does c come from, right? Well, this is some c between x and a. So not a lot of restrictions there. It ranges somewhere between x and a. So let's go ahead and find the Taylor polynomial of degree 3 of a function, and then I'm going to go ahead and write the remainder as a function of both x and c. So two things here. Taylor polynomial, and I'm going to show you how to write the remainder, which is an important skill. We're going to need this, of course, for our homework, quizzes, exams, life. All right, so as usual, let's take some derivatives, and I'm going to be evaluating at x is -5, right? So that's my a value here. All right, -5 everywhere. Only need up through 3. Notice we're doing a degree 3 polynomial, not a general nth degree polynomial or a Taylor series. So let's go ahead and start taking some derivatives. 1/2 times x plus 9 raised to the -1/2. Think about chain rule, but chain rule will be just multiplying by the derivative of x, which is 1. Take a second derivative. That -1/2 comes down. Take a third derivative. That 3/2 comes down. And you can see there's some nice alternating going on here. I'll move this over a little bit. And now let's go ahead and start plugging in -5. So -5 plus 9, it looks like we're going to be evaluating 4 to a variety of powers here. All right, so 4 to the 1/2 power, aka the square root of 4, is just 2. When I take 4 and I raise it to the -1/2 power, well, this would be 1 over the square root of 4. 1 over the square root of 4 is just 1 over 2. So I get 1/2 times 1/2, which is, of course, 1/4. Okay, let's do this again. -1/4, and I now have 4 to the -3/2. 4 to the -3/2 is going to be 1 over 4 to the 3/2. When I take the square root of 4, I'm going to get 2, and 2 raised to the 3rd power is going to be 8. Right, so this is 2 to the 3rd, aka 8. So 8 times 4 should be 32. So there we go, my -32. And then finally, a third derivative. So 4 to the -5/2. So this is going to be 1 over 4 to the 5/2. Take the square root of 4, I get 2. When I take 2 and I raise it to the 5th power, that's going to be like 32. 32 times 8 is 256. You can use a calculator or do this out longhand if you need to. So my final answer here is, well, I have a 3 in the numerator and then 256 in the denominator. Oops, yeah, battery low, that's fine. I should have enough to finish. So the 3rd degree Taylor polynomial of our function f centered around -5 is going to be, well, t sub 3 of x is equal to 2 plus 1/4 times x minus a. So minus a negative is going to be plus 5. Then we have my -32 over x plus 5 squared. And now we don't forget that we have to divide by 2 factorial, right? That's really how you calculate the coefficient. It's not just the second derivative evaluated at -5, but we also have divided by n factorial. So this one now needs to be divided by 3 factorial. It's a good way to make a small mistake and get some points off. So if we go ahead and simplify this down a little bit, You can see, ooh, some 3's cancel out here, and this is going to be 512. X plus 5 to the third. Excellent. So this is my third degree Taylor polynomial centered about -5 of our function square root of x plus 9. So, okay, what about the remainder? Right, so I'm going to use this remainder formula, which means I need one more derivative. R sub 3, we need the fourth derivative. So if you'd like to, this is the fourth derivative, 4 dashes, or most people would put a 4 in some parentheses, evaluated at some c divided by now 4 factorial times x plus 5 to the fourth. Okay, so what is the fourth derivative? Well, we take one more derivative from the third derivative, right? So we get the -15/16 times x plus 9 raised to the -7/2. So and we need to evaluate this at c. So instead of x, I suppose I should plug in c. So let me just erase this. There's my c. Divided by 4 factorial times x plus 5 to the fourth power. Now this is not a very satisfying answer, and we can simplify it down a little bit, but this is the remainder function that has to do with both x's and c's, right? So it's going to have x's and c's in it. So now let's simplify. Let's see, the 3 out of the 4 factorial is going to help cancel with that 15. Then we're going to have a 4 and a 2, so 8 times 16 is going to be 128 times c plus 9 to the -7/2 times x plus 5 to the fourth. So that's as simple as we can make our answer look. That is the remainder. And I understand this is a slightly unsatisfying answer, right? It's hard to tell exactly what this is giving us. In the next section, 11.11, we'll actually get a number out, which will be a little bit more satisfying. But for now, we have this. All right, and that just about does it for 11.10. I think we're all set to do our web work homework. I'll see you next time at 11.11.